First I may introduce the participants here. So my name is Klaus Nemmerzal. I'm from SAM, from the University of Bremen. Your name is Stefan. I have it here. Sorry. Xavier Kalmet and Domenico Giulini. And I'm supposed to talk here or to lead the discussion about what to sacrifice, and this is the question how to search for signals of quantum gravity. So what we are doing now is first I will give a short presentation to define the subject, to define the level where we like to ask this question, and then I ask a few questions to my colleagues here, and then the discussion is open and we can make your remarks and then contribute to it. Okay? Good. So, first slide reminder what we can expect from quantum gravity, then the strategy of how to search for quantum gravity effects, and this of course then is related to what should go wrong with the standard physics and what one should look for in the experiments. Then I will discuss a few specific topics, and then I will come to the discussion and to some questions. So this is what you all know. There's no need to go into details here, just to give the set of all attempts to quantize gravity. And here I have some modifications which one generally expects from a quantized theory of gravity. So one domain is that there should be some kind of fluctuations of geometry. This can be in various ways, so there might be a fluctuation in the space-time metric, and this may just be the Riemannian metric, or we also have this fluctuation in terms of the Finsterian space-time metric, which averages out, so that in the average there's still only a Riemannian metric. The connection may be an independent variable, and so it may show some fluctuations. So torsion may fluctuate in phenometricity. There have been various papers on fluctuation of the curvature, or even the notion of the space-time manifold disappears, and there's some kind of granularity as well. Some further thing what one expects in many cases is that there are in the effective equations for fields or particles there may appear higher derivatives. This comes from some non-locality, or this is a notion of a non-locality, comes from granularity of space-time, deformed symmetries, and so on. Usually one also expects some modification of quantum mechanics. There might be some non-linearities appearing in effective Dirac or Schrödinger equations. There may appear some non-Hermitian terms, and so on. In particular, in string theory, we expect the time dependence of constants, and connected with this, of course, also a violation of the University of Weak Fall, or the weak equivalence principle. We also expect, and this has also been discussed here, modified Newton and Coulomb laws at small and large distances, and there might be further general expectations what are possible general features from quantum gravity modifications appear. And if we take this, then one can show that in general this may lead to a violation of Lorentz invariance. So now we are on the level of the real experiments. So this is more on the level of the theoretical prediction. prediction, and now we are on the level of experiments, and this is now where we are now asking our questions here. So here we expect from most of these features that we have a violation of Lorentz invariance, a violation of the university of gravitational redshift. For example, this is related to time dependence of constants, universality of the university of free fall, and what might be interesting is that this might be different for the classical and the quantum regime. We expect anomalous dispersion effects, frequency effects, polarization, birefringence, and so on, and again modification of quantum dynamics. And here it is interesting that the first 3 points are together the Einstein equivalence principle, and according to general considerations, the Einstein equivalence principle predicts more or less the frame of standard physics, and then it is clear that since the quantum gravity is more than standard physics, more than general relativity, then the quantum gravity then should predict violations of the Einstein equivalence principle. So, and therefore, one of the strategies to search for quantum gravity effects is to look for violations of the Einstein equivalence principle. If you find some violation of this principle, then it's a good hint that this should be a quantum gravity effect. How one should look for quantum gravity effects or effects from new physics. Until now, all physics is, or all the experiments confirm standard physics, perhaps dark matter, dark energy. This is not standard physics, but it's recast in a certain form of it. So if we want to go beyond standard physics, then then we are searching for new effects, better estimates, or a larger parameter space. Then we can do this only by improving the accuracy of the current experiments, or by explore extreme situations, that is, enlarge the parameter space, or to explore exotic issues which are not in the focus until now. So the improvement of accuracy, I've given here you some examples. One is, for example, the Michelson-Morley experiment. So the best experiment for a long time was the Brie and Hall experiment from '79, and this measured the variation of the velocity of light with respect to direction of the order 10 to minus 15. This value was valid until 2003 or so, and nowadays the best value approach is 10 to minus 18. So within a few years they made 3 orders of magnitude improvement, which is really amazing. And as the experimenters told me, they are expecting to have in a few years then the accuracy of 10 to minus 20. And 10 to minus 20 is not so far away from 10 to minus 28, so they are really in a good shape. The similar, of course, applies to Kennedy-Zornack experiments. For the University of Free Fall, or the weak equivalence principle, the accuracy today is for the English parameter 10 to minus 13. This is from the Edelberger group in Seattle. And now there's this microscope mission underway. It is approved, and it is expected that it will go in 2014, and then it is expected that this mission will test the equivalence principle to the order 10 to minus 15. There was another proposal, STEP, and a further proposal, GG, Galileo Galilei, and this STEP mission was based on cryogenic technology, like the GPD mission, and the statement was that they should be able to test the equivalence principle to the order 10 to minus 18. Unfortunately, there is no activities anymore for the STEP missions. The US Space Agency does not like this mission, so we have to wait a few years more. There's also activities for testing the weak occurrence principle in the quantum domain with atomic interferometry, and there are proposals also to do this in space, and then one could expect an accuracy of 10⁻15. Clocks also showed a huge improvement during the last years and will show further improvement in the next year. So now they are having 10⁻16, reaching 10⁻17 accuracy, and they will reach in a few years 10⁻18. One major part of this improvement is the invention of the frequency comp. And so this then will, of course, lead to new tests of the universality of the gravitational redshift and also for the absolute gravitational redshift. By means of these new clocks, we will have new tests of the search for time dependence of constant, define such a constant in particular. And of course, we are looking forward to have the test with anti-clocks, that is a spectroscopy of anti-hydrogen. There's also a good progress in testing Newton potential at short distances with the neutrons. You certainly know this experiment by Abel, where there are the stationary states of the neutrons. You see the energy levels of the neutrons on the table. And there are other experiments in the preparation to improve tests of Newton's law at short distances. Also, the gravitational wave interferometers are a high precision device, which is of course made for testing for searching for gravitational waves, but perhaps they may also be used for other purposes. So the next point here is the exploration of extreme regimes. So we heard a lot about high energy regimes, the time of flight analysis, and regarding the dispersion relation. But also extreme low energies might be useful for search of quantum gravity effects. For the ultra-cold neutrons, but also with Bose-Einstein condensates, one may see influences from modifications of the dispersion relations or fluctuating space-time. Then we have the extreme large distances. For example, dark energy, dark matter is an effect which is related to large distances, or with gravitational waves from the very early universe. And of course, the time of flight analysis is also related to large distances, but also small distances are of importance. For example, Newton at the small distance. We have this long time scales. For example, the search for time dependence of the constants needs stability of devices for very long times, but also this idea of search for fundamental quantum gravity induced 1/f noise can be related to long time scales, because this adds up, and then we can see then the effect increases. We can have effects due to very large accelerations or to very small accelerations, and the very small accelerations then are related to the galactic rotation curves, dark matter, Mond acceleration, and perhaps this is also something which can be related to quantum gravity. And then also high intensities, as we had this morning. Then we can discuss a few exotic issues, for example, active passive mass, active passive charge. This is not very much in the focus of discussions, but it is on the very basis of our fundamental, of our theoretical description of nature. All this is a part of Newton's axioms on which all our theoretical understanding of the physics is based on. Then we have the order of the equations of motion is an issue of the classical equations of motion. the question whether there is an inertial system or not. If you have a fixed variance space-time, there is no inertial system, so this is also very basic assumption in the general relativity and non-relativistic physics. Then the relation between force and acceleration has been questioned with respect to dark matter issues, and there's also the question whether there's some maximal acceleration. All this is related to the issue of Newton's law, which, as I mentioned, is very basic to our present understanding in physics. So specific topics. So I will discuss 2 or 3 specific things here. One is the dispersion relation. Usually, the modification of the dispersion relation, which is here in this lowercase e, is of the cubic or quartic order or higher order than, of course, high energy phenomena are very appropriate to search for these quantities. But if this is if this e is linear in the momentum, then this term will be large compared to the other terms for small velocities, that is for low temperatures. So here this particular modification of the dispersion relation is very appropriate to be looked for in the low temperature experiments. So we have the question then of high versus low energy, and we can discuss this with respect to the dispersion relation, as I've done right now, obviously with respect to space-time fluctuations. And additional issue concerning the modified dispersion relation is the existence or the creation and the evolution of Bose-Einstein condensate. For certain certain modified dispersion relations, there might be some obstruction that the Bose-Einstein condensates can be created. So for this question, low energy physics is very appropriate. And the space-time fluctuations act somehow like a heat bath, so the coupling is different than usual heat baths. And but also here it is clear that that cold and clean quantum systems are very appropriate to see space-time fluctuations, and they also may lead to decoherence, and this also can be seen in the cold systems. Here, this is the drop tower in Bremen, where we are, and in this drop tower we can perform experiments. Inside the drop tower we have a drop tube, and here you see a capsule where experiments can be carried through under weightlessness conditions, and one of our experiments is a Bose-Einstein condensate in the free fall. And this Bose-Einstein condensate is created in free fall and then can expand freely. So we open the trap, and the Bose-Einstein condensate can expand freely. So on the left upper picture, you will see the Bose-Einstein condensate after 50 milliseconds, and on the right, on the lower right picture, you see the Bose-Einstein condensate after 1 second. Here some residual magnetic fields restrict one dimension, but it is freely expanding in the other dimensions. And the length in the z direction is 1 millimeter, so we have really here a macroscopic quantum system which has a huge dimension. And this has been published in Science a few weeks ago, and so we have now demonstrated the technology that we can create Bose-Einstein condensates and therefore macroscopic quantum system in free fall. And now we are going forward to do fundamental physics tests with this new technology. So in general, we will study these Bose-Einstein condensates, explore the parameters of this BEC and so on. We have the possibility with this freely falling BEC that we can obtain lowest temperatures. We can study the spreading of wave packets. It seems to be that there is no dedicated experiments testing the spreading of wave packets. We can make experiments for quantum reflection, quantum diffraction. This can also be used for a test, for a high precision test of a possible non-linearity in the Schrödinger equation. We are planning next to do a quantum test of the University of the Fall. This is of the weak equivalence principle. This is Bose-Einstein condensate. For that we will prepare two species Bose-Einstein condensates and then make two interference experiments in the same trap with the two different species. We can also look for coupling to a curvature. This has been discussed today already. So curvature is a proportion to the density of the source, and if you bring some high density material near to the Bose-Einstein condensate, then one expects a slight modification of the shape of the Bose-Einstein condensate. We can search for fundamental decoherence by observing the dynamics of the Bose-Einstein condensate. We can make local measurements, since this is here really a macroscopic object. We can make a local measurement and then look how the rest of the Bose-Einstein condensates will behave. And of course we can ask whether space-time fluctuations or modified dispersion relation have some influence on the dynamics of this object. And the plan also for the future is to bring this Bose-Einstein condensate in space so that we have really long evolution times, 10 seconds, 100 seconds, or so, how long it can. Here I have some comparison between astrophysical observations and laboratory experiments. You have seen that I'm in favor of lab experiments, so please forgive me. Of course, the astrophysical observations have the advantage that have access to huge energies, but there's no systematic repeatability of the observations, and you have no unique interpretation. This is so to say complementary to experiments in the lab. There you can repeat the experiment, you can systematically vary the initial and boundary conditions, and therefore can search for errors. You can improve the precision and so on. You can obtain ultra-low temperatures. You can have very clean tests, null tests, and some of the experiments already have quantum gravity sensitivity. For example, gravitational wave interferometers have already quantum gravity sensitivity. Okay, so I will come to the end of my short presentation here. So we all expect that there will be some quantum gravity effects or signals of quantum gravity. The scale of these effects are not known. There are effects certainly at the extreme large energies, but I expect also effects at the extreme low energies. A few questions is that it is sometimes if one imagines that we receive something, it still needs a discussion whether this really is a quantum gravity effect or can this be just a fixed force or something like that. What one should try in searching for quantum gravity effects is to be as far as possible independent from the theory and the model under consideration. What one really needs is some observation of some effect which does not fit into our present scheme, and this is but we already have some effect. This is dark matter, and what also is an issue with what can be discussed are whether there might be some fundamental enhancement factors. For example, for the time of flight analysis, the distance, of course, is an enhancement factor. For search of the 1/f noise, the long integration time is an enhancement factor. For space-time fluctuations, the holographic principle is an enhancement factor. Perhaps you have further examples of enhancement factors that will help in designing experiments. Okay, and what my point of view here is that I would here really my personal point of view is to promote a bit this lab experiments and also the issue of dark matter, whether this might be related to quantum gravity. Last year there was this huge discussion about this holographic noise, whether this could have been seen in the GU600 experiment. There was proposals by Craig Coleman that this was really the holographic noise, and there were also good suggestions from Jackman and Van Damme. I would suggest to think more on the cold atoms and clean quantum systems and the possible influences of quantum gravity on that. And I think that Giovanni will talk a bit on that on the Friday in his last talk. And I think, and he has right now this talk of Adrian Kent, that is very important to have more on quantum tests in the classical gravitational fields, and I think that can be learned much about from entanglement in gravitational field EPR type experiments from discussing and doing experiments related to the Schrödinger-Newton equation. An interesting thing certainly is the quantum classical transition and the search for fundamental decoherence. Fundamental means that it is not, you cannot avoid this as it would be, for example, if it's due to space-time fluctuations. So this is, so to say, the introduction here, and now I would like to start the discussions with my colleagues here, and yeah, I have the first question to Nico, how important it would be to have a better study of the quantum to classical transition for quantum gravity phenomenology.
Well, my subjective feeling is that it is very important. And it has been this, I mean, the semi-classical equations have been dismissed for several reasons, and there are good reasons amongst them. But I still think, and I think I'm very sympathetic with Adrian Kent in that respect. It does make sense to ask, at this level of our understanding or non-understanding of quantum gravity, it does make sense to ask questions like whether there are, for example, non-local correlations. And it does make sense to ask the so-called Schrödinger-Newton equation that you mentioned, whether we can, in molecular interferometry, see, in fact, some inhibitions of the spreading of wave packets according to what in the Schrödinger-Newton equation would be the self-gravity of a wave packet. So I would strongly support that sort of research, even though I am aware of theoretical difficulties with that equation, which may be partly relieved if you consider it as a stochastic equation, but even though in the naive sense, I would say it is important.
So I'm not sure we touched on this so far. What do you mean by the Schrödinger equation?
Oh, if you take the Schrödinger equation, it has a potential in it, and you say that potential in the Schrödinger equation is actually is the mass of the particle that you describe with the times the gravitational potential, and the gravitational potential is produced by the wave function itself. So it's the modulus square of the wave function times the mass of the particle that is the source of the Poisson equation in Newtonian theory of gravity. And then you plug into the Schrödinger equation, and then you get a nonlinear differential, integral differential equation.
But isn't the answer to this question depend on your strategy of what quantum gravity is? In the sense that, you know, if it's only trying to quantize the gravitational field as you did for any other field, then why would that question be important? If it's writing quantum field theory in curved space-time, then maybe the answer is different. So it depends on the strategy you want to pursue.
Yeah, that's precisely the point. The point is, it does make sense in a discussion about quantum gravity to study a situation where actually you don't quantize gravity. You just take the gravitational field to be a classical thing that interacts with the quantum system. That is, of course, a difficult, I mean, as we know, that's a difficult, a theoretical difficulty to have interactions between quantum systems and non-quantum systems. And there is no mention here of quantized gravitational degrees of freedom. And yet, it is a first step that teaches us something about the sort of interaction between classical gravity and quantized matter, of which very little is known. I mean, as Daniel, I think, also emphasized in his talk.
Apart from power experiment.
Yeah. Yeah, but I mean, as he made the point, this is just a constantly accelerating frame, whereas in the self-gravity, the wave make it would not be.
I ask a provocative question that is, or at least you can reassure me about this point. I mean, I'm always worried when we talk about quantum gravity, the fact that most often we assume standard quantum mechanics. It's a kind of dogma. And I know there are arguments about quantum mechanics here. Just to give you an example, in the de Broglie-Bohm interpretation of quantum mechanics, you may have the density is not equal to the psi square, you know? And maybe that in a situation where gravity is strong, this is not a good assumption. For example, I don't know how quantum matter gravitates in this case. Do we have an idea? So the question is not so much this, but I mean, is there an argument, or everybody of you knows an argument, why we should bother first about gravity and then about quantum mechanics? I mean, is there a hierarchy of scale? Something that we can really talk about quantum gravity and assume that quantum mechanics is safe?
Well, here's the reason. The reason is that if we make the hypothesis that underlies the Schrödinger-Newton equation, which is semi-classical gravity, which has its weaknesses, that's certainly true. But one point is, it makes predictions about certain deviations from standard quantum mechanical behavior that are within the range of molecular interferometry. And therefore, it makes sense to ask that question. Or in that sense, it makes sense to ask the question, because we can actually make experiments for it. Nobody said that this would be the only possibility, but it is one.
How, I mean, so far, just trying to address your question, I'm not saying that certainly question also quantum mechanics why simple, but just trying to find some possible way of addressing your question. I mean, so far we have evidence that quantum field theory, as someone, maybe Daniel was mentioning, so far has worked, quantum field theory has worked pretty well. We don't have any evidence against it. And then when talking about gravity as compared to other interactions, well, in principle, when you look at low energies, gravity doesn't really have a clear incompatibility with quantum mechanics or quantum field theory by itself. It's just a matter of when you try to find the UV completion, that you have some difficulty. That the UV completion of the theory is non-trivial. But so in that respect, it's not so different from other interactions. So you try to marry gravity with quantum field theory, and at low energies, it's not terribly different. It's not so different from other interactions. It's just that when you try to find the UV completion, it's highly non-trivial.
But I'm worried exactly about the strong gravity. When we go toward quantum gravity, I mean, you approach a singularity, you approach a very strong curvature regime. Do we have really a bulletproof argument to say that quantum mechanics as we know it is safe?
What answer is no? No.
I have a comment and slight disagreement, perhaps not slight, with this view that gravity, in some sense, the only problem with gravity is that in the UV we have this non-normalized.
It's not the only issue.
No, I think there are basic conceptual issues that we have completely out of reach. We cannot imagine, or I cannot imagine, what would it mean to face a situation in which I have a superposition of two metrics. How would that feel? How would matter behave in that condition? I have no...
That's an answerable question.
Huh?
That's an answerable question. I mean, we have
Well,
a theory of quantum gravity that can work in regimes where we observe superposition of atoms or whatever, and that's effective gravity.
No, but the question is about strong gravitation.
Well, in a strong gravitation, case, we don't know. But your question was conceptual.
Yes.
Can we even imagine what that would look like? And the answer is yes. I think we can. You said that, and as far as I know, that this approach has, well, it has a lot of potential, but has a lot of it is yet to be explored.
Because I don't know even how to talk about the place. You know, when I think of a superposition of
Yes.
electromagnetic
So
fields,
that's
I say in
an
this
explanation of
particular
the-
place I have a electromagnetic field that is in a superposition of these things. When I have two different metrics, perhaps you can teach me, but I cannot imagine it. But and let me make one more point. I think this inflationary situation is the only situation on which we really have not only a theoretical, but at least an observational, phenomenological setup where we have used at the same time general relativity and quantum mechanics to explain data that we observe. It's the only situation that I know of
Yeah, but it's
experimentally.
specifically this approach, where you just take quantum, linearize or perturbed gravity as a quantum field theory, and then
But
use
knowing how to
standard.
calculate and knowing how to interpret are two things, from my point of view.
Well, once it depends what you calculate. That's what
Yes. There is a slight confusion here. One is quantum mechanics, the other is quantum field theory, which are not identical, because quantum field theory is one step more than quantum mechanics. Okay. Then, clearly, I mean, Stefan asked the right question. Stefan asked, see, you know. So let me try to answer in a historical way. The reason why people start with quantum mechanics is because we simply tested it in the absence of gravity and it works very well. So people like to preserve things. However, when people look quantum mechanics in the presence of microscopic black holes, they modify it. And that is by the non-Hamiltonian theorem. That's what led to the coherence, right? So that's the first step. However, what is quantum mechanics? The EPR to me is the crucial key to understanding, because I believe that when there is strong gravity regime, even the concept of a state gets the vacuum of the vacuum of quantum mechanics in the weak gravity regime is probably not the same as in the strong gravity regime. So
When you talk about black, now we are talking about here.
that's what I mean. So what you're asking quantum mechanics, that's what my question. What do you mean by saying quantum mechanics? You mean the Schrödinger equation, or you mean? I mean, what do you mean? You mean what do you define as quantum mechanics? That's.
I think that discussion should not be entered. Because
Yeah.
If we're going to comment on things at this level, I think that there's a very big distinction which has to be made between using quantum mechanics in laboratory kind of experiments where we have a lot of experience with it, and the very extreme assumption that we can apply quantum mechanics to the universe as a whole and study cosmological questions which are not about isolated systems using the same mathematical formulas that we apply to laboratory systems. I think that I wouldn't make the case here, but I think there's a very strong case that extrapolating the methodology we use for laboratory systems where the observers in the process of the outside to the universe as a whole is fallacious. And I'm very, very skeptical. I mean, having worked a lot myself on the subject of quantum cosmology and solutions to the concerns, but I'm very skeptical. And it also is an area where, in addition to the foundation problems of quantum mechanics, there are several very daunting foundational problems having to do with the meaning of observables, the nature of time, and so forth, which are quite distinct from the foundational aspects, issues of normal quantum mechanics that I think makes me very, very hesitant to believe in the notion of quantum mechanics applied to the universe.
But we have data. The difference we have data.
We have data for ordinary quantum mechanics.
No, we have data from the spectrum of the cosmic microwave atom.
No, sure, but I think it's fair to say that that could all be construed as taking place in an isolated system. So there's none of those calculations in which the CMB is related to quantum fluctuations and inflation used in an important way to deal with the Witt equation or address the issue of the of the normalization of wave functions in the universe, the issue of observables, the issue of there's a whole nutty field of quantum cosmology where things like eternal inflation, when people get into big messes, which what's the measure, what's the norm, what's the physical interpretation, and it's precisely because we do not understand if we can meaningfully apply quantum mechanics to the universe as a whole, that there's this whole wacky subject of eternal inflation.
No, but even before that, I think there is an issue. There are people who believe it. It's only when you look at the microwave background, which is really
Crazy.
it's going to be stupid. But there are people actually believe it and they respect it.
And what about all of history before a few years ago? When we looked at the microwave
So
background?
of course the question there is, what is the prescription then? If it's not the usual one, why is it? Why is it different? Why is it right?
No, I don't have an answer to the question, but I think that there's a big difference between applying quantum mechanics in laboratory experiments of the kind that our chair was discussing earlier, where I think we can be pretty confident that I don't believe myself in quantum mechanics, but I think we can be pretty confident that deviations in quantum mechanics are very small. And the whole extrapolation of quantum cosmology, which brings to us into confrontation with a whole bunch of other foundational problems.
Let me try, so Hiroshi, to answer to your question. Just try to mess with quantum mechanics in this context and then publish a paper. Won't do it. So it's easier to mess with.
No, I mean, I was saying
Survive.
Well, let me try to come back on my point. I mean, one thing is that, you see, this is also an opportunity. We're talking about quantum gravity phenomenology. We always stress the gravity phenomenology beyond Einstein. But how do we know, for example, that different interpretation of quantum mechanics, equivalent interpretation normally of quantum mechanics, this degeneracy split in strong gravitational fields? Let me just do an example, no? And that you may have a phenomenology which is present in one interpretation of quantum mechanics that at that point is no more just an equivalent interpretation, it's a different picture of how the world is. And maybe that there is an opportunity here, no? That maybe that if we can look at phenomena which are the imprint of this regime in which gravity was strong, it was influencing quantum matter, truly quantum matter, we may see the fingerprints of this phenomena. This is an opportunity and it would be from the point of quantum gravity phenomenology something we should look at.
The problem here is that the two candidates for the interpretation of quantum mechanics, like Bohmian mechanics or collapse theories, are really hard to relativize. So you don't have relativistic Bohmian mechanics. In Bohmian mechanics, basically, there is a preferred frame. It's not detectable, but there is one. So, already once you try to consider these alternative interpretations, you already smuggle into the discussion things that these interpretations bring into the game.
But this is great.
Yeah, that's fine. Yeah, okay.
And I mean,
See what this is correct.
It's fine, but you have to remember that if you go in Bohmian, then you import the preferred frame ab initio into the game.
No, and Anthony Valentini's whole point is that if you go out of equilibrium, out of Bohmian equilibrium, you can see the preferred frame. You can see
So you have phenomenology of the kind. Well, it's another kind of phenomenology, but it's quantum reality phenomenology because it's also thinking that this is coupling when you have these strong fields that somehow is strong gravity that is bringing out.
Yeah, that's true. The preferred is not detectable in Bohm only in this initial equilibrium state.
Right. But the imaging that strong gravity, and this is one of the conjectures that is more credited, that is bringing out a view out of the equilibrium. Maybe in the early universe, some effect that we are overlooking. I'm just saying that, you see, it's very complicated. I'm not saying that, but if someone has an argument for telling me, look, these effects are impossible to see, or there is a hierarchy of scale, you will have much earlier gravity, quantum gravity effect rather than quantum mechanics violation effect, then that would be another interesting problem.
I want to mention, I'm not trying to do propaganda, but unfortunately you forced me. This is an issue we have been studying.
We had an agreement that made me before.
No. And it's precisely this issue in cosmology. You don't need things to be strong gravity. You just need the gravity to be strong enough to be relevant. And in the formation of the initial perturbations, you can ask these questions. Do you use collapse, or do you use some other stuff? And depending on what you use, the spectrum can change a little bit. So it is a fact that modifying how you treat quantum mechanical situations in the early universe.
What do you mean exactly? The spectrum changes with what?
For example, when do the modes collapse? Depending on according to which pattern the modes collapse, you can change the spectrum from the Harrison-Sadovich to modify the spectrum.
So usually people say you lose the phase, blah blah blah, and you become real. Is this relevant?
Yeah, well, for what? Are you going to collapse in the field, or in this momentum conjugate, or in some combination of them? And at what time each mode? All the modes at the same time, different modes at different times, will they cross the horizon, will they don't?
So
And these things modify the observational spectrum.
you simply modify the amplitude?
Sorry?
It modifies the amplitude, the actual.
No, it modifies the form.
How does the probability?
Sorry?
You mean it's not Gaussian? It depends on Gaussian.
No, the form, instead of becoming flat, the fundamental spectrum.
It's the amplitude, yeah.
Yes, yeah, but not the overall amplitude. The amplitude as a function of K, of L.
Okay, yeah. Okay, but at the risk of representing a one-person minority point of view, okay, I'd like to kind of comment on some of the remarks made earlier, mainly the question of whether one should question quantum field theory or even quantum mechanics in the context of gravity, right? Now, I'd like to put forward perhaps a particle physicist point of view in this context, okay? And as particle physicist, I mean, you kind of grow up with quantum field theory, okay, so this is what you learn from the childhood on, okay? And I mean, the other input here is certainly, I mean, knowing that physics is an experimental science. Right? So all quantum physics, which is experimentally verified, is particle physics, okay? Now, what's so great about quantum field theory in this context, okay? It works extraordinarily well for spin 1 half and spin 1. Yes? These are the particles which have been observed, yes, which have been measured, where we know that these theories have a nice high energy behavior, which is nicely under control. This is a fully fledged global quantum field theory, which has all the proper semi-classical limits. Okay? I mean, in essence, the vision of linking classical with quantum physics is fully realized in this setup. Now, where are the weaknesses? Weakness number 1 is spin 0. Spin 0 particles have not yet been observed as fundamental particles. Okay, so there is, I mean, that's one of the reasons probably for why LHC has been built. Okay, they want to find this particle and identify it as a fundamental excitation, okay, and place it as correspondingly to the quantum field theoretical setup. Good. So that's spin 0. Now, if you think in terms of spin, gravity is obviously spin 2. So if you immediately start about thinking just coupling a spin 2 thing to the standard model, it would mean that this must be a theory of the metric field. Fine. Now, if you'd like to play this game further, say more than spin 2, okay, people know that you run into horrible difficulties, because if you want to couple higher spin, you actually need infinitely many spins, so this is why people kind of are not looking into this. Okay, so borderline spin 2 is a theory which potentially, right, carries all the right properties as we know from spin 1 half and spin 1, except that people got frustrated by trying to quantize that theory the way theories have been quantized previously. Okay. So, from a particle physicist point of view, the question, I mean, the situation is extraordinarily annoying. Yes. On one side, quantum field theory works extremely well, but then perturbative quantization of gravity seemingly doesn't fly. Okay. So the question, in a sense, is there a fundamental trouble with quantizing spin 2? Now, if you have a hard nail to nail that, I think I would be extremely pleased to give up on either
quantum mechanics or quantum field theory is a conceptual framework. Okay? But as long as this is not completely named, okay, and so I probably agree that there is no hard answer as to whether spin 2 can be quantized one way or another in the usual quantum field theory framework. Okay? So as long as this is not the case, I think it is fair and natural, okay, to still raise that question in the quantum field theory framework. So I mean, okay.
So I was also trained as an elementary particle theorist and a wave field theorist, and I think we're way, if I may, way beyond that issue. I think we know this, if by conventional quantum field theory you mean background dependent, where the field expansion and the inner product and the regularization procedures and everything all depend on a fixed background metric. We know why that doesn't work. We know it doesn't work because it contradicts the gauge invariance of the full theory, which is whether it's general relativity or supergravity or those theories coupled to anything. The genius of the quantum field theory of the 1970s was to understand how to realize precisely the gauge invariance of Yang-Mills theory. And that led to the standard model and so forth. And I think the lesson of if there's an obstacle to realizing precisely the nonlinear gauge invariance, you take it very seriously, is the lesson. So one, we understand why it doesn't work. Two, we understand some things that work better. Nothing has gone all the way. But for example, just if you take out of the quantum gravity, the result of the construction of the spatially diffeomorphism Hilbert space, the spatially diffeomorphism of Brane Hilbert space, which realizes the the spatial part of the diffeomorphisms. There are precise theorems, rigorous theorems that tell us exactly what that Hilbert space is, and tell us how to regulate and construct spatially diffeomorphism Brane operators. Now there are issues going to space-time diffeomorphism Brane. I'm not claiming that everything is done. But I think we know, one, what breaks down in the usual perturbative quantization precisely, because one can say in as much detail as you want what goes wrong and why it doesn't work. And then there's an example of something that goes one step further, and that at least points to us a direction, and the direction is that the excitations are extended objects. And that, interestingly enough, is the lesson also in string theory, etc., that to construct consistent quantizations that have that approximate or realize some aspects of the spin 2 field, you have to go to a situation where the excitations are extended objects, and that's the lesson of either quantum gravity as far as it goes, or string theory as far as it goes. So I would hope that we even if we recognize that we're not all the way there, we absorb those lessons. We don't keep trying to do the conventional quantum field theory that works so well with ordinary gauge systems.
Oh, no, I fully agree with that. The point I wanted to make is, people have understood provided perturbative quantization doesn't work, okay? But this doesn't mean that quantum field theoretical quantization doesn't work.
Well, fluid quantum gravity is a application of gauge quantum field theory to the case where the gauge invariance is included in what the invariance.
No, okay, you have a point that, if this goes through, then you even have something which
No. Fundamentally, the structure of the Hilbert space is fundamentally non-perturbative. Again, I'm being very careful with my words. There are important, very frustrating open issues with the structure of the product level of the full space-time diffeomorphism invariance, the realization of the full space-time diffeomorphism invariance. I'm not claiming anything is done, but I'm claiming as much as what's done is done by exploiting what I think is really the lesson of the 70s, which is taking non-linear gauge invariances very seriously. Okay. In the structure of the Hilbert space, the structure of the operator algebra, the structure of regularization.
How would you feel if you found out that n equals 8 supergravity was finite?
Fine.
That shows you that the conventional approach works.
No. You mean finite in conventional perturbation?
Yeah.
Yeah, so that would tell me that there is a theory, a very, very constrained theory of very, very constrained by symmetries where one can compute some observables, I would still not take that to be, that perturbative definition to be the fundamental definition of n equals 8 supergravity. I would take that as a motivation to find a deeper quantization that preserves all the gauge invariances, which are even much larger. That is, the supersymmetry is a gauge invariance, it's not a global invariance. And I would seek to understand in a non-perturbative way the action and the structure of the Hilbert spaces that are invariant under that fuller gauge invariance. But I would take it as an encouraging result. And sure, I mean, anything new is good.
Okay, then we have.
I want to make two short comments to your question, which I'm thankful for because it's, there is always this discrepancy between the relativist point of view and the particle physicist point of view. One remark is a pure spin 2 theory, linear theory in Minkowski's way, is classically inconsistent. And that tells you that if you took it very seriously upon quantization, then you would not be quantizing a classical theory that can stand on its own feet. So that would be a little strange if you think of quantization being a procedure that should be applied to a classical theory that's at least intrinsically consistent.
Excuse me, can you explain why it's inconsistent classically?
Well, because let me just make the second point. And the second point is there is a conventional wisdom what goes wrong with spin 2 theory if you quantize it. So there's a loop, one loop calculation, and then the statement is there is a divergency, but the divergency can be removed by field redefinition, which is local. Then you make the 2-loop calculation, and you find again a divergency, which is a cubic polynomial in the curvature tensor, and then the statement is this cannot be removed by local field redefinition. But it can be removed by non-local field redefinition. I was trying to ask people in the last half year or so, particle physicists, what is wrong with that? What is wrong with a non-local field redefinition? And I got very, very different answers, to my surprise. So I think there is still, even in the community of particle physicists, where these sort of techniques are sort of everyday business, there is still a discrepancy on what we should call a sane and an insane theory.
No, not at all. I mean, this is crystal clear.
That's what everybody said, but the answer was so different.
Okay, I'm aware of meta. So I want to couple meta to my theory. When I couple meta to that theory, the theory is perfectly dead. So there is no ambiguity.
I want to make a comment actually. This is on camera.
You can do things as non-local, introducing non-local fault functions. This is something you can do, okay? But this boils down to become equivalent to introducing higher derivative operators, right? With arbitrarily high order. Yes, I mean it's technically possible to do that.
Yeah.
Oops, the last remark, and then we should go to other topics.
Well, so this was just a comment to this aspect and the answer. So if you're really interested in understanding what's happening in the deep UV regime, then yeah, I mean this was of course not the answer. But nevertheless, if you're interested on the other hand in the infrared regime and you want to deal with perturbative quantum gravity around a particular background as an effective field theory, then I would say that the way we understand effective field theories nowadays, I would say that there's not much of a problem with that, at least as far as this point is concerned. So this is just a little remark. Of course, this is just in the infrared regime. If you are interested in what's happening in the UV as a fundamental microscopic theory, then there's nothing to say about that.
The scattering matrix, if you make a non-local field redefinition, the equivalence theorem is not working. So the scattering matrix changes. And therefore, once you lose the uniqueness of the amplitude, because that's what an experimentalist measures, and that's what I would call a quantum field theory, effective theory, whatever. Amplitudes. A non-local field redefinition does not leave the amplitudes invariant. But now, of course, this doesn't mean that the theory is wrong. It simply means that there is one configuration. God knows whether it converges with all the loops or whatever. That is a physical thing. But the beauty of the prototype field theory, if you like, is that the amplitudes are independent of your local field definitions. And then, but that's the only thing that I have to answer what's wrong. Not wrong, values.
So when I was I have a colleague at Penn State who's I think to be a very good field theorist, John Collins. And I was amazed, I had a discussion with him once about addressing a particular issue with inflation, basically cosmological perturbation, particular to very unstable supergravity theories, okay, so things that people didn't like. And his attitude was kind of interesting. His attitude was, we need to develop a new language to deal with this. Now, of course, this is a person who knows a lot about renormalization and knows a lot of quantum field theory, but I really enjoyed the fact that he immediately didn't dismiss it and say, well, it didn't fit into. He understood that quantum field theory is a particular language, and that language could be extended, and this framework may call for the development of a new lingo, so to speak. So that's one thing I wanted to also add in with that. We have certain, well-defined toolkit that's proven to work, but it doesn't mean that now that when we have new systems under study that we might have to extend our language. Your case about inflationary perturbations and decoherences, I think, are a great example of that. One other thing I wanted to add, I think we also should really respect the wisdom of experimentalists. I think that one of the things that I personally have really benefited from is to actually take these types of issues directly to my friends that actually build real experiments. Because tantamount to a lot of these interpretational issues is the way they actually build an experiment and the way they actually deal with systematics. So I think, like, for example, having people like Brian with us, Brian Keaton, who will talk about polarization and how, what he has to pay attention to deal with the issues that Joao and Lee are calculating with the amplitude by refringence, is going to be very enlightening, for example. I'm looking forward to learning, because that, I think, affects how interpretational issues may actually, as Stefano pointed out, could actually influence what we actually need by quantum gravity, what we're looking for. Getting that wisdom from our experimental friends. And the last thing I want to add, is what it seems that, like, one of the things I think is really cool about this meeting is we have a sense of an awareness of assumptions that we made about what quantum mechanics is, what gravity is, and we're shaking it, so to speak, shaking it up, and just saying, well, okay, we may not have a complete theory, but we know what to look for, and let's just go full on and try to do something. But I think that there are hidden assumptions still, and the best historical example of this is the 40-some-odd years it took us to figure out superconductivity, given the 1911 experimental observation of it. And all along, and I got it from the horse's mouth, Leon Cooper told me this, which was, people assume that the ground state of a quantum system is stable. And it took them just basically realizing, oh, there's an instability in the vacuum, and I have a non-perturbative ground state that superconducts. It was that simple realization that led Cooper to the instability. So what are the hidden assumptions that we're making that we're just afraid or we're just blindsided? I don't know what it is, but I'm just bringing that to light.
I think you point towards another problem. That is, historically speaking, very little has been discovered without theoretical guidance. Mm-hmm. Unless people are told what to look for, it's very difficult to find it. Now, since we don't know what quantum gravity is about, it's very difficult to guide experimentalists. And that's why I think we've not made progress on the theory side either.
But that's why I think it's good to actually go to the experiments and say,
sure.
Because sometimes they have anomalies that they just that's just a systematic.
But that's the point. If they're not told that we're seeing of something interesting, they won't see it.
Yeah. So Brian, for example, was telling me something on the at the airport that I was just like, wait a minute, that may not be he was talking about leakage from one mode to the other, and that's something like, even as a theorist that claim that I do cosmology, whatever, I was really unaware of, right? So Because we think when you guys are going to measure, like, you know, a particular effect, it's a pure, you know, it's pure in the sense that there's no leakage from a T to E, right, for example.
And you might make predictions that require capabilities that we don't have and we may never have. Testing, you know, the CMB at L equals 2. We may never be able to do that in a clean enough way. We might be a requirement to validate some of these predictions. But these things are exciting. We need these to justify things like CMB calls. We need beyond the inflationary gravitation.
So what do you think about, for example, one of the things that cosmologists hate to ever do is go in the high L regime, like, you know, at very small angular scales, because like there's a lot of nonlinearity and noise and things get washed out. But this is exactly a sweet spot for ground-based experiments.
Yeah.
Do you think that we should be, that one can potentially find a clean quantum gravity effect there? Is that crazy?
Well, I think looking for scale dependence is critical. You want to disentangle the effects from lensing, which will be your biggest contaminant in high L. So if you can't disentangle or make a prediction for how you can discriminate between quantum gravitational effect and lensing, which will occur at radically different scales.
So probably the clearest you need to be so the quantum is a bad example. Also high L is bad example. Sometimes you can do.
Sometimes, yeah. The sweet spot is probably between the super horizon L 80, 70, up to about 1,000.
Of course. I don't want to be provocative, but okay, the difficulty with quantum gravity, as we know in 4 dimensions, is that the scale, the force is very weak and the scale is very large.
Give it up.
No. If we are lucky and there are extra dimensions and the scale is low, TV, then we will have a wonderful laboratory in 2 years' time to test probably the most obvious problems of how to form the black hole and how they will evaporate. Then you will have that problem at your disposal. If, of course, usually Murphy's law will tell you that probably is 1,000 TV and we'll have to wait for the linear collider. But, you know, you make stuff.
I'm willing to put money against
Pardon?
I'm willing to put money against that possibility.
How much?
We can't do this.
Well, why should I? Ask Savas to put them on. But, you know, maybe if there is, if there is, yeah, I know. Well, there is nothing against it, okay? I mean, you dilute the theory, I mean, by making it in the higher dimension, and then the scale would be this. Then you would test, because you would produce the macroscopic black hole.
I mean, another thing that I think one hidden assumption that I just realized today was a hidden assumption in all my thinking about quantum gravity, based on the meeting today, was that space exists. Like, what if, like, you know, so Faye pointed out, like, she believes, I'm going to put her on the spot here, that only time exists, or causal relationships exist, and there's no space. So what do I mean when I perturb a gravity wave, if only time exists? And, you know, there are formulations of quantum gravity where that is the case. So, you know, I mean, I would say that.
So hang on.
Yeah.
If a massive gravitational wave hits me, what is actually hitting me?
That's how I felt. I would feel if Muhammad Ali hit me. I wouldn't know.
Exactly. So if the time only time is hitting me, then I wouldn't feel that, because it's just, you know what I'm trying to say.
Yes.
This is crazy. Okay, I shouldn't say crazy, but it's problematic. You see.
It is, but it forces that question, though. Right.
But perhaps we can change shortly to an observation which has been done by you in the dark matter. So the question to you, do you think that dark matter has something to do with the quantum gravity? I think there are some discussions about the modification of inertia due to quantum properties and so on. So there are some ideas which may lead to confusion.
First of all, dark matter is interesting because that's the only non-speculative motivation to extend the standard model of particle physics. There is no candidate. Sorry?
You don't believe in anything having to do with mine?
Okay.
So
well, I would consider that as an extension.
Okay.
In any case. Now, I think that, okay, I thought a bit about it after you raised a question during the break. I see two ways dark matter could have something to do with quantum gravity. One would be actually a very minimal way to have dark matter. These are primordial black holes, and that's something that has been studied. And the latest papers I've seen claim that it could work if it explains all of dark matter. So that would be a beautiful way. The sun, to have black matter. The sun model is fine, it's just gravity that provides further matter in some form. The other one is much more speculative. Is modification of the 1/r potential through quantum gravity, and I think Reuter is one of the people who look into those things, how RG improvement of Einstein could lead to effectively a Mond-like story. But I think even if you do the calculation seriously, Mond has troubles with bulk clusters. My understanding is that they have to add some part of dark matter to make it survive. So I think it looks less attractive. So there are two things. Now, the other thing is that I think quantum gravity could have also very interesting implication for model building of dark matter. Most of the time, people assume that you have to posit some new discrete symmetry to prevent the dark matter from decaying. But we know that discrete symmetries are typically violated by quantum gravity. So that could tell us that you have a new form of gauge interaction in that dark matter sector. And you could learn something about quantum gravity and a new force of nature, because quantum gravity could make your dark matter decay too fast. So that is the two options I see where quantum gravity could impact that matter. Otherwise, it's a scale problem again. If we are in a conventional model where quantum gravity is at a Planck mass than 18 GeV, dark matter is probably a lower energy phenomenon.
I have a comment and a question. The comment is, it seems to me that modifying the 1/r potential is probably not enough, because we know we need dark matter to generate galaxies, right?
The Mond
to have things growing at the
the Mond
fast enough.
I mean, I'm not going to defend Mond, but I think that attempt was to explain dark matter just by modifying the 1/r potential.
So it's not enough to put the logarithm there, which will be basically what it's.
I'm having trouble hearing you.
So it's not modifying the potential, because that would have a length scale, not an acceleration scale. And the phenomenology of Mond is always around an acceleration scale.
Sure, but I mean, okay, the only comment I made is that this modification calculated by Reuter resembles Mond. That's all.
Yeah, the reason is very simple, because you have the running coupling, and because you only evaluate it over a finite length scale, which corresponds to the size of whatever these clusters. Okay, yes, this effectively can mimic quantitatively the effect of an acceleration. So this is why quantitatively.
But don't ask me to defend either approaches. Okay.
And the question, sorry, and my question was, when one wants to consider something like primordial black holes, have people considered what would their effect be in, for example, nucleosynthesis? Because I know if I put a little bit, an extra neutrino nucleosynthesis mix destroys the correct.
I'm not an expert. I do hope so. I do hope they've done that. I don't know.
So the question is whether they were cold at that time.
Black hole. I know the answer.
Yeah, you see.
You need to, if in order the density of these black holes has to be much less than the dark matter density, otherwise you would extend the MEV scale of the nucleosynthesis. That's why it could be part of dark matter. It could be part of dark matter, but not the 27%. Not the 27%. At least we think
the statements I read and were that it had to be all or nothing.
All cannot. I mean, that's what I'm telling you.
Within conventional
defend their. Within all cannot be is ruled out because otherwise you disturb nucleosynthesis, and then you will tell me fine, I disturb nucleosynthesis, and then it's a disaster because we know it works very well, right? I mean, the heavy elements.
I see your point. So
I
now,
have a comment. I actually think it's obvious. It would help much more in the case of quantum gravity. If it was,
Sorry, I couldn't.
It's obvious it would help much more in the case of phenomenology of quantum gravity. We have not dark matter but the modified gravity theory. Because you're basically saying GR is wrong. You've been quantizing dark matter. And then, in addition, there are most known theories, modified relativistic regime, the biometric theory. And the biometric structure immediately changes completely the perspective in which you've been analyzing the quantization of gravity. So I think, I agree, there are problems with clusters, there are problems with phenomenology, the non-phenomenology, but from a conceptual point of view, the idea that the basic classical theory of gravity is to be only good.
look, if you ask me where we put my money, I mean, all the particle physics models that people are designed to address the more, I mean, the hierarchy problem and so on, have natural dark matter candidates that are far less far-fetched than any modification of GR. So if I had to put my money somewhere, I would bet on a particle physics extension of the standard model to explain dark matter.
So if I put my money somewhere, I would not experiment. Because I think it's ultimately it's not a matter of taste, it's a matter of experiment.
Exactly, but look, I'm asking to speculate about quantum gravity and dark matter, so...
So why not jump in here while we're being speculative? Because I like very much what Stefan said. And so if space is really emergent, if time is real and space is really emergent, which I like, and there's more and more workshop which supports that, then like anything that's emergent, there should be defects. And if space is emergent, locality is emergent. And if locality is emergent, there should be defects in locality. That is, there should be from time to time some defect where you can jump from here to somewhere very far away because they're really connected at the Planck scale. And it turns out these things are ubiquitous with quantum gravity. In fact, it's one of the issues with quantum gravity. It's very hard to get.
Sorry, do you like it because it is ubiquitous in quantum gravity or other way?
It is a fact that it's ubiquitous in quantum gravity. It's hard to get rid of, to the point that it's a dangerous issue for quantum gravity. Okay. But while people are throwing speculative things around, so this is mostly not my work. This is work of Fortini, Marco Polo, and Chandra Prescott Weinstein, and a couple of other people, that dark matter and dark energy could be manifestations of the defects of locality, the disordering of locality. But I should also say that, like a lot of these speculative ideas, it's very hard to push it far enough to the point where it's publishable. For example, to where it can compare with Mond as a phenomenological law.
So I think it's obvious to get close.
Mond is not publishable.
Right, and what's hard to get is the connection between the scale and the cosmological constant of the dark energy scale. That is, the thing that would be very exciting is to understand what's implicit in phenomenology, which is the relationship between quote dark matter, the phenomenology of dark matter, and the phenomenology of dark energy. That's already a problem, even if you believe. And if I put my money somewhere, I put my money on there's just some particle out there which is dark. But there's still the question of why should the length scale, which characterizes when you need a deviation from ordinary Newtonian gravity with visible matter, why should that deviation be an acceleration scale, which is related to the scale of the dark energy? Even if you're a totally conventional vanilla dark matter person, you have to answer that question. You have to answer why the constant, which is measured in the Hubble-Fisher relation, is so close to the Hubble constant of the dark energy scale.
There are coincidences that we don't understand. We call that hierarchy problems, and that's what we try to solve. That's why we try to extend the standard model.
Something that John Schwartzman said to me, which I think is advice worth passing on, is that I always took seriously coincidences. There are no.
Well, that's why we try to extend the standard model. That's why we build a large collider to understand what stabilizes the Higgs mass.
No, sure. So, but the coincidence between the scale of dark energy and the acceleration scale, which denotes where you need the dark matter or non-deviation, is sitting there waiting for.
There are funny coincidences. You can relate the Planck length to the technical constant. Also, there are beautiful relations that give you these numbers. Whether there's anything deep behind that is another question.
Okay, I would bet a lot that there is something behind that case. And especially, and the reason why I would is that the Tully-Fisher relation is so well satisfied. There's so little, relatively little scatter around, which suggests that.
But I think it's fair to say that in a way, Mond was designed to explain galactic phenomenology. So it does very well galactic phenomenology. And then he does atrociously badly with clusters. And he gets so contrived when you get to the cosmological perturbation theory.
It's terrible.
In fact, the vector field which appears there is dark matter. We allow dark matter through the back door.
No, I'm totally unimpressed with any of the relativistic versions of Mond. I mean, to me, what Mond is, if Mond is right, it's saying that there's a component of the gravitational force where the force falls off slower than 1 over r squared, which is just screaming non-locality to you.
No, but I think you missed the main ingredient, which is it's actually what triggers this effect is an acceleration. It's not
No, I haven't missed that. That's why I haven't published anything.
So when I said this will be a matter for experimentalists, I think it's going to be solar system.
Well, I think I should also mention that even in the non-relativistic limit, fails in an unexplained way in certain setups. I mean, it can describe a large quantity of, say, clusters, but once they start to have an unconventional or unusual shape. Once they have an unusual shape, I mean, Mond doesn't work.
But that's because you have to integrate the equations properly.
Even it's dirty physics in a certain sense, where it's not that easy. I mean, I wouldn't be so scared about that. Many comments are the one thing, but there is some signal that is coming out from the observational literature, from phenomenology of dark matter, and is that there is a growing evidence that at least in galaxies there are some kind of unexplicable or universal relations between what dark matter does and luminous matter does, which are contrived from the point of view of, these are objects which have different evolution and so on. So for example, there are relations between the density of dark matter in the core is related to the bulge that the distribution of the luminous matter. And there is a growing evidence in this direction that somehow is telling you that there is kind of a universal relation between the dialogue between dark matter and luminous matter that cannot be simply explained in a very easy way, given that the object underwent a completely different relation. And regarding there is a comment regarding dimensions. I mean, one way to recover is to introduce theory to dimension theories. So in a sense, and I agree which even in emerging fiction, it's very difficult actually when one has many fundamental fields to emerge one single metric. You may have a basic, it's not generic. I mean, for example, this Anner's model of gravity, generically you get a multimetric system. And then, rarely, when the microscopic system has some fundamental symmetry, or some tuning of the parameter, which is another way to call it, you get a monometricity. So I would say that it's rather natural in this mindset to ask this kind of. Then I agree with you that there are still many problems. See, also the phenomenology is very weird in this sense. It's very difficult to extrapolate.
No, come on. I mean, you just want obviously is that you have one parameter, only one. I mean, you have an extremely strong, convincing, possibly dirty, but nevertheless phenomenology. Some phenomena where if not convincing.
We're not discussing the famous simple dark matter in the rotation curve.
I think what's interesting in what you say is that the metrics are actually not conformal.
Disformant.
You have to do disformant.
Yeah.
And I think that's the remarkable thing about one. Because I'm not conformal metrics I think about it. In fact, we have to say
Okay, first we can now slowly come to the end because I think for the 6 we should stop until therefore 10 past 6. So I thank you all for the discussion, and then I will go.